for an adiabatic flame we have the unburnt enthalpy should be equal to the burnt enthalpy, which means we could now say sigma k equals 1 to n yk comma u times hk u equal to sigma k equals 1 to n ykb hkb, where hkb is now the enthalpy of the burnt products, ykb is something that we have seen so far. So what we then do is the normal thing, which is we now say enthalpy is formation enthalpy plus sensible enthalpy, right. So using heats of formation and sensible enthalpies, we can write sigma k equals 1 to n yku minus ykb times delta hf naught, which is the reference formation enthalpy for each species, equal to, now we look at the sensible enthalpy, which is T ref to T TB, that is CPB dt minus integral T ref to Tu CPU dt, right. Our job is to actually find out TB given Tu, okay, that is what you are trying to do here. So where of course CPB is equal to sigma k equals 1 to n ykb CPK of temperature, and CPU is sigma k equals 1 to n yku CPK of T. Now, so what we want to do is we want to try to find out what this is, right, and therefore and then we have already looked at how to do the products, therefore we can do the same thing. So we had dyk divided by nu k double prime minus nu k single prime times capital Wk equals, for over many species to let us say one particular species dy1 divided by nu 1 double prime minus nu 1 single prime times capital W1. So integrating this, we get yku minus ykb equals, so let us suppose that you do this for the kth species in relation to the fuel. So that means you take any kth species and then you take fuel on the left hand side and right hand side respectively, then you could write this as yfu minus yfb times nu k double prime minus nu k single prime wk divided by nu f wf. Now keep in mind your nu f here is actually the stoichiometric coefficient for the fuel, and you don't have any fuel on the right hand side, therefore your nu k double prime minus nu k single prime for the fuel is simply nu f, right. So you don't have to worry about that anymore because you know how the reaction looks like for this. So from here if you know this difference now for the kth species, multiplying by delta H of k and summing over all k, sigma k equals 1 to n yku minus ykb times delta H of k naught is equal to, then you see the only thing that's really getting summed over on the right hand side is this part, alright, and all this is independent of k, it's only for the fuel. Therefore yfu minus yfb divided by nu f wf times sigma k equals 1 to n nu k wk delta H of k naught, where we now use the symbol where of course it's going to get a little bit bigger, so we try to compress it by saying nu k is nu k double prime minus nu k single prime. Just to kind of have our bearings on, when we say nu k is equal to nu k double prime minus nu k single prime, that's like a set that you're trying to allocate a particular symbol, but we have also looked at a nu without a subscript, which is a stoichiometric ratio, mass ratio, and nu f is actually the stoichiometric coefficient for fuel that's already been identified, which is basically this one evaluated already, right. So these are the different nus that we are looking at, so just don't get confused about these things. Alright, so if you now look at this, then the left hand side here is what this is. Effectively what it means is this essentially translates to just looking at this summation, alright, and therefore if you now say that summation, if it is q, so we can now define heat of combustion q equal to negative k equals 1 to n nu k wk delta H of k naught, alright. Let's just see heat, or the other way you can do is you can also say negative sigma k equals 1 to n nu k delta capital H of k naught, where this is on a molar basis, this is on a mass basis, so mass basis multiplied by the molecular weight is what you're looking at there. So so for simplicity, let us now say Tu equals T ref. Now we have already gone through this before in the context of premix flames, but it doesn't really lose much generality here by doing this, and also assume constant Cp, therefore now for a lean mixture, when y of b equal to 0, right, that means you're running out of the burnt fuel because you don't have any of it as an excess as for a lean mixture, then all you do is you now say here just plug in y of b equal to 0 here, right, that's what you would actually do for the left hand side. On the right hand side this is simply Cp times Tb minus Tu effectively, right. So that means the Cp can come to the other side in the denominator, and then you will get Tb minus Tu equal to Q YFU divided by Cp nu f Wf. Okay, Now it's not for nothing that we chose to actually look at fuel as one of the sides of this equation. So in this equation we chose one of them to be fuel, with the other one being any kth species on the left hand side, because we are looking at a lean mixture where you are going to substitute y of b equal to 0. But for a rich mixture you would want to actually substitute YO2b equal to 0, right, which means we need to have a place in which we can substitute YO2b equal to 0, for which we should have started out having oxidizer integrated rather than fuel, right. So that's what we would do. For a rich mixture, we go back and integrate again as YKU minus YKB, trying to redo this again with oxidizer on the right hand side instead of fuel. So YKB minus YKU equal to YO2 U minus Y, so this must be YO2U minus YO2B divided by nu O2 W O2 times times nu K WK divided by, yeah, that's it. I'll rewrote this. So nu K of course is again nu K double prime minus nu K single prime, which I had not done before. So if you do this and of course you now can take this step where you multiply by delta H of K and sum over, and then you now recognize this as Q and plug this back in here and write your TB minus TU. At that stage you now plug your YO2B equal to 0, right, for the rich mixture, and plug YO2B equal to 0 for rich mixture, right. TB minus TU is equal to Q YO2U divided by Cp nu O2 W O2. Now what we are really looking for is the burnt temperature in terms of the mixture fraction Z, because mixture fraction is kind of like our basic function now. So we want to now represent this in terms of YFU in terms of Z and YO2 U in terms of Z, which is not very difficult. Okay, so we can say that this is basically Z times YF comma 1, and this is 1 minus Z times YO2 comma 2, right. So we know how to do that. So we now write YFU and YO2U in the above expressions in terms of Z, the mixture fraction, then right, also the unburnt temperature in terms of mixture fraction. How does that work out? You have Tu of Z equal to T2 minus Z times T2 minus T1, right. How do I know that this is right? T2 is the oxidizer stream temperature, and T1 is the fuel stream temperature, right. So if I now plug Z equal to 0, then it's all oxidizer, then I get the unburnt temperature for the oxidizer stream to be T2, that's what this is. If Z is equal to 1, then it is the fuel stream, right, then the T2 gets cancelled and you get T1 for the unburnt temperature, so that's the temperature of the fuel stream. So this is basically like a linear relationship between the two temperatures for the unburnt temperature of a mixture of any given mixture fraction in between, right. So if with that being the case, you now go back and plug that in terms of Z, and then plug your Y of U in terms of Z and YO2 in terms of Z, right. So all of them put in terms of Z will be then TB of Z equal to T U of Z plus Q Y F comma 1 divided by Cp nu F Wf times Z with Z much less than or equal to Z stoichiometric, or Tb of Z equals Tu of Z plus Q YO2 comma 2 divided by Cp nu O2 WO2 times 1 minus Z for Z greater than or equal to ZST, right. Now the maximum temperature, you can calculate the maximum temperature. So as Z keeps on increasing, you see Tb will keep on increasing up to ZST, and when you now cross ZST, you now have to use this expression where as the Z keeps on increasing, Tb keeps on decreasing, right, and at Z equal to ZST you should actually get the same expression from both. That means you should have like one temperature at which the stoichiometric mixture has a burn temperature. So the maximum temperature, and that will be the maximum temperature. The max temperature TST is calculated for ZST from either expression above. So how does this look like now? We've been drawing these pictures at every now and then, as and when we get a bunch of expressions in terms of Z, we try to plot them. So here you see if Z is plotted along the horizontal axis, and let us say go from 0 to 1, all oxidizer stream here and all fuel stream there, and let's say the oxidizer temperature is T2 and the fuel temperature let's say is T1. The unburnt temperature is not going to depend on whether you had a stoichiometric surface and so on, okay, whatever it may be, you just get a straight line that connects the two, which is basically following this expression. That's a linear expression in Z as well, okay, and you just get a straight line that connects these two. This is Tu. As far as burnt temperature is concerned, you have to now worry about whether you're fuel rich or fuel lean, right, and that means you have to look at where your ZST will be. So if your ZST is going to be here, then the TST is going to be the peak, and on the one side when you're now having only oxidizer, you don't have any reactions, you're simply not having any fuel at all, so you go back to T2, right, and similarly on the other side you just have to look at a linear variation from TST to T1. So it just becomes that simple, alright. So in some sense what this really means is we can now put the whole picture together in what we are doing in a bigger graph. Let's just try to do that now. Need more space. So let's now say we had a unburned situation and a mixing field in which you have the Z varying along the horizontal axis going from 0 to 1, all oxidizer to all fuel, right. And we now want to look at how this proceeds in a third axis where we are interested in constructing the same kind of picture for the burnt process. So let's suppose that that's what it is, right. And along this third axis we now have a variable called reactiveness. What's the level of reaction that's going on? How do you monitor this? By looking at YF minus YFU divided by YFB minus YFU. So when you started out, alright, when you started out you have YF is equal to YFU, so R is equal to 0, okay. When you end, YF becomes YFB, therefore R becomes 1, alright. So we can plot this along this axis, maybe let's say along this axis, maybe we just plot along this right. That's the way the reaction is going, all right. And YF is turning into turning from YFU to YFB. Initially we are having your YFU actually starting from, let's say, YF1 here to 0 on this side, and therefore you're going to have a straight line that looks like this. So this is your YFU, all right. And somewhere in here you're going to have your ZST, right. And your YFB is going to be so maybe you can look at, you don't have to worry about ZST at all here. You just to get a perspective on how this kind of a linearly increasing YFU actually turns out to start increasing up to YF1 over here, right. And similarly you could think about a YO2U which starts from YO2 and goes all the way to 0 when Z goes to 1. That's the unburned oxidizer, right. And that now is going to go all the way to, so this is also YO2, and of course I should have marked YF1 there, right. And then we could do a couple of things. One, let us assume that you have diluent only in the oxidizer like in air, right. So more the air, more the oxygen, and correspondingly more diluent. If you don't have any air, you don't have any oxygen, you don't have any diluent either, right. So you could now think about a diluent concentration that is going to grow with more and more O2 as we go along backwards in this axis, starting from 0. So this is like YDU, where D is for diluent, right. And this picture is not going to change at the end of the reaction, it's about the same. So you're now going to get this picture to look like YDU, right. And of course there is a value here that corresponds to how much diluent you have for how much oxygen. So this could be, for example, 0.23, that could be like 0.77, and this could be now 0.77, all right, okay, and so on. Then we talked about temperatures. Oh no, I think we talked about products. So we talked about products. We don't have any products here to talk about, all right. We're talking about products only here, and the way we talked about it is we now said you're going to have your Y CO2b go like that, and Y H2OB go like that, all right. And finally we talked about temperature. So in the temperature we can plot two things, the unburnt temperature and the burnt temperature, right. So the unburnt temperature, let's suppose would be, we now pick a scale like that, this is your T2 and this is your T1. It's as if like the fuel stream is colder than the oxidizer stream, right, it could be. And then you can mark these 2 points, T2 here and T1 there, maybe T1 is somewhere there according to this, and now going to go all the way to TST and go back here. So if you think about it, this is like what we were saying for the vicinity of the Burke-Schumann flame. So in the Burke-Schumann flame, if you have a diffusion flame sheet in the Z axis, it's going to be located at Z equal to Z as T, right, and from Z equal to Z as T the temperature is going to fall on either side, on the fuel rich side one way and the oxidizer rich side the other way, right. But in the flame we are looking at how it is behaving in space rather than in the space as in the physical space above the burner, rather than looking at it in what is called as the mixed diffraction space. So in this picture everything looks very nice straight lines, okay, all linear dependences in the mixed diffraction space, but that's not how the curves were looking like in the physical space, and that's one of the reasons why the mixed diffraction space is quite valuable. So question basically now is how do we transform this into, or how do you utilize this in the physical space system? That's what we are worried about. Like for example, if somebody is giving you a burner and asking you to find out how the flame is going to look like and how the species concentrations and the temperatures are going to vary and all those things, you can't give them a picture back like this which is in the mixed diffraction space. You have to now translate this into the physical space. So you now look at how the mixed diffraction, for example, can be utilized in looking at the spatial variation. That means we need to have a governing equation for how the mixed diffraction varies in space. That means we have to have an evolution equation for this. What I'm going to now write is basically the steady state counterpart, but there is nothing that really stops you from doing an unsteady counterpart, just like how you would do an unsteady Schwab-Zeldovich formulation which we did not go through, but we said it's possible to do so. So similarly we can now write, for example, a evolution equation for the mixture fraction, right. So the mixture fraction essentially is like a conserved scalar, and it is now being evolved by convective and diffusive processes. Okay. Now that's the physics behind how this goes. You can actually derive this mathematically in two different ways. One, go back to the definition of mixture fraction. Mixture fraction is nothing but a fuel mass fraction kind of notion, right. So you can now find that you have like a nu YF minus YO2 divided by something, or plus nu YO22 divided by something. So all the things that are getting added up and divided by are constants which depend on the inlet concentrations, but what's really happening is you're now forming this coupling function like nu F minus nu YF minus YO2, right. If you now use the evolution equations for species concentration YF and YO2, and you now multiplied by nu, subtracted one from the other, added something else, divided by something, some other constant, and so on, you should now be able to get this. And while you do that, you can also find out that the right hand side being the reaction rate term is now going to get subtracted out, pretty much like the way we did in the Berg-Schumann problem. So in the Berg-Schumann problem we started looking at the Schwarz-Zeldovich species equation with the reaction rate on the right hand side, and we now try to normalize things and subtract and form the coupling function such that you get the same expression on the right hand side, so that when you subtract you get to 0. So you get 0 here similarly. The other way of looking at it is, while we were looking at the mixture fraction, we also noticed that we could form element mass fractions, like for example ZC, ZH, ZO, and so on, and we could form our mixture fraction based on the element mass fractions. So long as the mixture fraction is essentially defined based on the element mass fractions, and in a combustion process the chemical reaction that we are going through conserves elements, it does not really destroy the elements. So no matter whether carbon is present in the hydrocarbon or carbon dioxide, no matter whether hydrogen is present in a hydrocarbon or water, no matter whether oxygen is present as itself or as part of carbon dioxide or water, right, the mixture fraction gets conserved because it is based on element mass fractions, and therefore the reaction rate term will not show up when you now try to write a evolution equation for this. So we just write this out as it is, and then the other thing that we need to do in order to actually look at the structure of the frame. So this is okay as far as the infinite chemistry kind of approach is concerned. So what we talked about in the Berg-Schumann problem was that this is like a sheet that corresponds to infinite chemistry, and on either side you have these things dropping and varying correspondingly. But if you want to now think about finite rate chemistry, okay, so if you are to think about finite rate chemistry, you have to have the reaction rate show up somewhere, and typically the problem with finite rate chemistry is the finite chemical reaction depends on species concentrations as well as temperature, right. And in the Schwarz-Zeldovich formulation what we have noticed is we have to keep the reaction rate at least in one equation even while you are subtracting a lot of other things. Therefore if you now say let's now we have to consider the energy equation where the reaction rate depends on the temperature as well as concentrations, and the concentration is governed by equations that have been subtracted from each other to get this. Okay, so this represents a pair of species reactions, the species equations, and then we have the energy equation. So if you now write this as so this is of course before we do that we can say this for a simple case of let's say the Berg-Schumann kind of problem. If you now say rho u dou z divided by dou x minus right? Or if you want to do it in cylindrical polar, this would be like this, and 1 over r and so on, that is okay, equal to 0. Now you could go ahead and solve this as it is, and then finally look at the solution and find out wherever z is equal to z as t is where the flame shape is in terms of, so you're now going to get finally z of r comma z equal to z as t is the flame shape. Right, so you could go ahead and do your solution that way, and once you do this, on either side in the burner, let's say you have your flame like this. This is your z equals z as t. You can now get the solution to give other z values. And so on. That picture looks very good, isn't it? Right? That's how it actually turns out to be. You can solve the Schwab-Zeldovich formulation and get this kind of picture. And so these will correspond to different values of z, with z equals z as t being where it is to correspond to where the flame is. And then you can now look at, for different values of z, what should be your YFB, what should be your YO2B, what should be your TB, and so on. All right. So you could do this, but that's actually the infinite rate chemistry approach. Now for the finite rate chemistry approach, as I said, you need to have at least one equation which contains the reaction rate. That means you have to have the energy equation, let's say minus 1 over r dou by dou r rho d dou t by dou r, right, equal to 1 over Cp sigma k equals 1 to n delta H of k naught Wk. This is directly coming from our Schwab-Zeldovich energy equation, right? Now what we have to do next, and I'm not going to do this in great detail, I'm just going to point to directions that will take you there, because this is just getting a bit too involved, and I think the idea is essentially made and we could leave it there. So what you now do is transform the equations with respect to z. That means we could say let one of the variables, let's say z here, equal to z, which is the mixture fraction, and let's say r is equal to z1. So no big change there, just changing symbols, but here we are actually changing meanings, okay, and this is kind of like what's called as the Krokot transformation, where you are replacing one of the independent variables by a dependent variable upon which you want other dependent variables to depend. So in all that we have seen so far, all the dependent variables that we are talking about are depending upon z, and z itself is governed by this, given that it's depending on x and z and r, right. So once you know how z depends on the spatial variables, we now transform our equation in terms of z, capital Z being the independent variable, and now try to obtain the energy equation in terms of capital Z. Get your solution in terms of capital Z. If you know how Z varies, you know how your temperature varies, right? So this is not so trivial. You will actually end up with lots of, so essentially what you have to go through is, like, if you now want to say dou by dou Z, then that's actually dou by dou Z plus dou capital Z by dou small z times dou small z, and so on. So you have to apply chain rule across, and you have to bring in the dependence on capital Z everywhere by chain rule, and then you plug this in these equations, and this actually becomes a fairly huge term because of this, and you'll have lots of cross derivatives and so on. And then you could make now an approximation. You could make an approximation whereby you say gradients that are perpendicular to the flame are important, gradients that are tangential to the flame are unimportant. This is typically valid whenever you have a flame sheet kind of situation, right? And you can now throw away a lot of terms, and to leading order you can even throw away terms that are there in other derivatives except these. And finally what you will get is, so neglect tangential gradients, and you will now get something like rho chi divided by 2 dou squared T by dou capital Z squared equal to minus 1 over Cp sigma k equals 1 to n delta HF naught K WK, where chi is 2d dou z by dou z the whole square. Okay. In general, in 3D you could actually have this as a gradient squared, gradient z squared, and this would basically be called this is basically what is called as a scalar dissipation rate. And this is essentially looking like a diffusion term. In fact, the scalar dissipation rate has dimensions of 1 over time, and essentially it gives it gives the characteristic diffusion time scale, right? And basically it tells us how the diffusion happens. Z is mixed diffraction, keep that in mind, and you now have the gradient coming in picture. That means it essentially represents the transport phenomenon of mixing. Okay. How the mixed diffraction variable is now going to decay because of diffusion, right, while the mixing happens between fuel and oxidizer. And this is actually quite important in turbulent diffusion, wherever you are looking at, for example, scalar transport by turbulence. Then you have the turbulent diffusion, mass diffusion coming into picture, and the scalar dissipation rate under turbulent conditions would be quite important quantity there, but at the moment let's not worry about all those things. And the point I wanted to make is, it looks like you have a diffusion term and a reactive term, and the effect of this would be to try to find out what goes on in between, in a very narrow region in the Z space where things are varying due to finite rate chemistry, and that's the effect of this. Okay. And what you will find is, in reality you don't really have the oxidizer concentration come all the way down to 0. It could leak across the reaction zone if you now take finite rate chemistry into account, because it's not able to consume all the oxygen, right? It's not really infinite rate reaction. Now, and then it will look like this is like essentially a diffusive reactive balance. that we saw for the reaction zone in the premixed flame, and I also pointed out that this region is going to be like the reaction zone in the premixed flame, and whatever is outside of this in the near vicinity is going to be like the preheat zone in terms of transport processes dominating, except it's going to be radial transport versus axial convection and so on in the Berg-Schumann problem, or any co-flow diffusion flame problem like jet diffusion flames and so on, except this is not really a diffusion term alone. You have it actually as a function of as a second derivative of capital Z, which is the mixed diffraction. So this is a derivative in the mixed diffraction space, so it is a transformation that contains within it convection as well as diffusion. But by making this transformation in terms of the mixed diffraction, we have essentially enabled it to look like a reactive diffusive balance, alright, but the transformation contains in it the convective and the diffusive effects. So we would like to stop here and then we can pick up on let's say droplet combustion from next class.